Hi everyone and welcome back to PrepFusion. I am Anish and today we will be discussing about speed control of DC series motor and also braking of DC motors. So previous lecture we discussed completely about speed control of DC shunt motors. We learned two methods. One was the uh, control using armature voltage, control of armature voltage. Another one was the flux. We were controlling the field flux. So in this video we will learn about DC series. So again the voltage equation, I mean the generated voltage or the back EMF equation, that does not change, right? For series or shunt, also the flux also does not change. I mean, like flux change, but what do I mean? I will explain. So let me put a series motor here. Okay, so in this case what will be the back EMF will be proportional to flux and the speed, right? And your uh, torque will be proportional to flux and Ia. But in case of series motor, as we know that your flux is proportional to Ia, because whatever current is flowing through the supply armature, same current is flowing through the field winding. So here my torque will be proportional to Ia square. Torque will be proportional to Ia square. So what I can say is, here as well, basically my back EMF will be proportional to Ia into N. So what can I do? What can I control? I can control the armature current, right? I can control the armature current. So what I will do, I will just simply connect a external resistance here. So basically what will happen, the current will go down then. So what I can do is I can connect an external resistance. If I connect an external resistance, what will happen? If I connect an external resistance, then ultimately let's name it as R external. So basically what is your current Ia? Ia will be Vt minus Eb divided by Ra plus Rac plus R external. So here what I can comment is that uh, yeah, here I can comment that if suddenly a external resistance is connected, the denominator will increase. Assumption is currently there is no change in EV, so denominator increases, Ia will decrease. If Ia decreases, this will decrease. If Ia decreases, flux is also proportional to Ia only, because it is the same current, right? As the, like, field winding current is the same as the armature current. So flux also will decrease. If flux decreases, the torque also will decrease heavily. If torque decreases, what is happening? So my net torque, right, is net torque is the developed torque minus the load torque. So this developed torque has reduced. That means what? There is net deacceleration, because the developed torque has reduced. So there is net deacceleration. So it is Td minus Tl. So there is net deacceleration. So what will happen? So hence the speed, due to this, the speed will reduce. If speed reduces, Eb will reduce. If Eb reduces, what will happen? Basically the armature current again will go back into a steady state, whatever was it, steady state, right? So basically speed is reducing. So this is used to control below base speed, because the more external resistance I will add, torque will reduce only. I cannot increase the torque, only current can decrease, current can go above. For that I need a negative resistance, not possible. So this is known as the armature resistance control that is used to control below base speed. Okay, so yeah, that was the armature resistance control. There is another way of controlling, right? Let's say if I want to go above, if I want to increase, what can I do? If I want to go above, or like, okay, like there is another way in which we can control it basically. Sorry, there is another way in which we can control it. The armature voltage basically, both of them, these are armature voltage control only. What we can do, instead of connecting a R external in series, we can control it R external in parallel with the DC series motor. So I will connect an external resistance in parallel with the DC series motor. Okay, so this is my basically current. So what will happen now? The current has been diverted, right? Now the current has been diverted basically. So if I connect a parallel path, what will happen? Overall, if IA current was flowing through here, bit of current will flow through here. Now this will be I diversion, and this will be IA dash. So my IA dash will be lower than IA because it has seen a relative path, right? I mean alternative path. So the rest of the current can flow through here. So basically your armature current reduces. If your armature current reduces, then your torque is phi into Ia. Torque, then this time the reduction is torque is lower because flux is still constant. Because assumption is overall Ia, I will make it constant. Ia will be constant, right? But as I am connecting a parallel path, so this Ia dash, actually the current through the armature, that will be reducing. So torque again will be reducing. If torque is again reducing, there is again deceleration. That basically means speed reduction. Speed reductions. These methods, armature voltage control, will be used for reduction in speed. Okay. Both this is known as the armature diverter control. Armature diverter control. Okay, so these are used to control below the base speed. Okay, so yeah, we will try to see with the workings. So yeah, as in DC series motor, the armature current and field are the same as the field winding is connected in series with the armature. This makes it necessary to carefully distinguish between the methods of voltage control and field weakening. Here also we will do the same. We will use the armature voltage control and the field weakening, but we have to be very careful because the armature current and the field current both are same. Controlling speed will involve varying applied voltage to the entire motor, or like varying the applied voltage by changing the armature voltage or by alternating the field strength. So we can insert a series resistance, as we discussed. We can insert diverters with parallel with armature as well as with field windings. We will see that in the next portion. Connecting multiple motors in different configurations. So this also we will discuss how connecting multiple motors can actually help us, okay, for speed control. So this is what we just had discussed, that if I connect a external resistance in series, what will happen? Basically the speed will keep on reducing. Okay, speed will keep on reducing. So basically if I am connecting an external resistance, so for the same amount of current I am getting a lower speed because the flux has reduced. So basically what is happening, what is my torque proportional to? Torque is proportional to phi into Ia, right? So if I assume that if I am connecting a R external, then overall previously phi is what? Phi is basically proportional to If, correct? Phi is proportional to If. So if I connect an external resistance, what will happen? The If will reduce because the Ia has reduced. So if both of these have reduced, that means the torque overall will reduce. So for basically overall torque that I will get will reduce. Also the speed also reduces. So basically the plot, right? The plot here will be, it is used to control for speed below the base speed. So what will happen, as I will keep on increasing my R external, the value of R external, if it keeps on increasing, what happens, the speed graph will go down. So if you remember the torque speed graph of a DC series motor, it was somewhat like this. It was somewhat like this, that this is speed, this is torque, and let's assume this has to be the rated condition. So where my R external is 0, so it is the rated condition where my R external is 0. Okay, now sorry, this is not, sorry, speed will be here, torque will be here, right? Speed will be here, torque will be here. Now if I keep on connecting more resistance, let's say this is some RE1, then I connect another resistance RE2, right? So basically what I can comment is that I am slowly increasing my resistance value. So basically RE2 will be greater than RE1 will be greater than 0. So the graph will simply shift down because the speed will be lower, right? As I keep on increasing for same current, the speed will be lower because I am producing less amount of flux. Okay. So it is used to control below the base speed. So this is the rated speed. Okay. Okay. So same graph will happen here, but quite the opposite, because as I keep on increasing my R external, so most of the current will flow through here. If I keep on reducing my R external, most of the current will flow through here, so less current will flow. So the what will happen, if less current is flowing through here, the torque here will be more and more lower, right? If torque is lower, it will deaccelerate more. So in this case, the difference will be that the diverter resistance, right? So here what will happen, this will just flip. So this is also used for controlling below the base speed, but here the difference will be, this will be RD1, this will be RD2. Okay, and it will go in the opposite direction. So this will be the point where my RD is infinity. Okay, because if it is infinity, all of the current will flow through here because it will not find any alternative path. So then I will get my rated speed because all of the current will flow through here. If all of the current flows through here, the torque is proportional to phi Ia, because flux is constant here, because here the current is not changing, only here we are getting an alternative path, so current is changing. So what will happen is that current will be the highest, okay, when RD is infinity. Now if I reduce my RD, so if I reduce my RD, let's say to 100 ohms, so let's say this path resistance is, let's say 1 ohms, so bit of current will flow through here. So as there is reduction in current, so there is reduction in current, so there is reduction in torque, so there is deacceleration, so speed will reduce. Okay, so that is what will happen over here. Okay, so yeah, same thing what we are discussing here only. So yeah, so if I slowly reduce my RD, what is happening, the speed is reducing. So here the relation will just be opposite, so RD will be greater than RD, d1 will be greater than r d2. So I will have to reduce my resistance so that speed also reduces in the same direction. Okay, that is just the difference in this characteristics and in this characteristics. Rest everything is almost same. Okay, so in this case, how will you solve the questions? How will you solve the questions in this case? So here the important factor to note is that what is my back EMF and torque proportional to. Okay, so same thing, right? My back EMF EB will be what? EB will be, you will apply the same principles. EB will be VT minus IA into RA plus RAC plus R external. Okay, and your torque will be basically equals to KT phi square, which is IA square, because same flux is flowing through them, right? So it is IA square. So this is how you can equate your relation. And like how will you solve the problems? So let's say you have a load where the load torque varies proportional to speed cube. You have a torque like that where the load torque varies proportional to speed cube. So what you can do, you can say that at steady state your load torque must be equals to the developing torque. So basically I can say that IA square will be proportional to N cube. This is one of the relationship that you will get. Next relationship is here. It is lying here. So basically I know my EB is proportional to flux into speed, right? From here I can directly say what does my flux depend on? Flux depends on current. So I can say EB will be proportional to IA into speed. So from here you can find out the relationship that this is one of the equation and this is the other equation, and from here you can solve the questions. Okay, so they will give you this information. This will be given the characteristics of load. Okay, this will be given in the question. Okay, so that's how you basically vary using armature voltage control. Now let's discuss how you can use field control. How can I use field control? So again the same thing, many things we can do. So there are many things we can do. So we have to control the field. I want to control the field. So basically EB is proportional to phi N and torque is proportional to phi IA. So if I want to control the field, first method is the easiest one, simplest one. What I will do, I will connect a field diverter resistance. So there will be a resistance in parallel, that is R diff. Again the same thing. So armature current does not change, IA is same, but here all of the current does not flow through the field winding, bit of the current flows through the diverter. So IA is diverted. Okay, so that means what is happening? Sorry, not IA, sorry, ISE is diverted. ISE is diverted. If IAC is diverted, then the overall flux reduces, right? So here what you can do, don't look at the torque. I will explain why you don't look at the torque. What is my speed proportional to? Speed is proportional to E by flux, right? So here if flux reduces, hence my speed will increase. Why? Because here, right, E is what? E is V minus IARA, and this is constant because IA I have assumed to be constant. This is constant here, right? That's why the numerator is constant, denominator is decreasing, so speed will increase. Okay, in the previous case you might have the same question, sir, why were we seeing through the torque, why were we not seeing through the EB, that this first relation, right? Because IA was not constant. As IA was not constant, EB was not constant. So here, right, we have to look at the torque. Here IA, EB not constant. In this case it is constant. In the field control case it is constant. Okay, so here it is constant, so that's why we will look at this equation directly, because it is very easy to understand, because the numerator is constant, denominator is reducing, so speed will increase. So it is used for control of speed above the base speed. Okay, that is the case one. Now just one second, is it a constant torque drive or constant power drive? So here Ia is constant, Ia is constant, hence the EB is also constant. EB is equals to V minus IRA. So it is a EB into IA is constant. EB into IA is constant. That basically means it is a constant power drive. Okay, it is a constant power drive. I hope you have understood this basic thing, and it is used to control above base speed. Okay, that is the important point. It is used to control above the base speed. What are other ways through which I can actually change the flux in the series winding? So this was the first one. Second way, what we can do is we can provide few tappings. Okay, so what kind of tappings? So here, right, that is present in the diagram. So I can change, like I can provide few tappings, and from here only I can connect the other end of the wire. Instead of this connecting directly, I can connect either this point or this point. Okay, so basically then what will happen, then I know that the number of turns, let's say, is n series total, right? If I am tapping from here, then the number of turns reduces, so it becomes n series dash. So basically the mmf, what is mmf? So although the current will be same, mmf will be, here current is same, right? Same current IA is flowing, so mmf will be n series dash into if, right? So this is still constant, that is IA only, same, but I am changing n series dash. So if I am changing n series dash, that basically means that n series dash, of course I cannot increase the number of turns, I am tapping it, so n series dash will be lower than n series. So the what will happen, mmf will reduce, if mmf reduces, that means that means uh, that basically means that basically means what, that means the flux has reduced, right? Because flux is equals to mmf upon reluctance, so flux will reduce. If flux reduces, again the same analysis as the previous one, so speed will increase, because IA current is not again changing, IA current is still constant, same current is flowing. IA, I'm not doing anything with IA, so IA current I'm not changing, so speed will increase. And third way to do is, actually it is kind of similar, is the second way. What we do, we make few divisions of the winding. Okay, we make two halves of the winding, we either connect them in series or in parallel. Okay, so we make two halves of the winding. So let's make two halves. So the first half will be n series by 2, and the second half will be n series by 2, and either we connect them in series like this, or what if we can do, we can connect these windings in parallel. So then what will happen, then through each of them the current will be IA by 2, IA by 2, and the turn number of turns is NSE by 2, NSE divided by 2. So what is the mmf, total mmf? Total mmf will be NSE into IA divided by 4 into 2, so it becomes half, NSE into IA divided by 2. Previously it was NSE into IA. In this case, it was, here the mmf was simply, because it was NSE by 2, because here first winding has half number of turns, current is IA, plus NSE divided by 2 into IA. So this will be the mmf. So this value will become NAC into I. Okay. So that is basically the MMF that we can conclude from here. So MMF in the case 1 and case 2 are different. So of course again I am reducing the MMF, so speed will also increase. So flux is getting reduced, phi is getting reduced, so speed will be increased because current will be same. So basically my EB into IA will be same, so this will be constant power drive. Torque will change. Torque will be basically inversely proportional to the flux, or because torque is phi into Ia and Ia is constant, so torque is inversely proportional to flux, and yeah, that is basically it. Torque will vary, torque will change. Okay, so yeah, so this is constant power drive in the previous case, right? So this is not constant power, this is constant power drive. In the previous case it was constant torque drive. Okay, that is what was happening. In the previous case there was a negative feedback that if the flux was reducing, armature current was reducing. So previously we connected a external resistance, due to that what happened, the armature current reduced, right? So if armature current reduced, what happened, then there is a feedback. So that due to that feedback what happened is that there is deceleration, then the back EMF reduced. If the back EMF reduced, then the armature current again increase. So as due to the feedback what happened is, initially the armature current was reducing, then the armature current increased, and my flux is proportional to the armature current only. So reduction and increase, it makes the torque constant. So this was the case where the control was constant torque drive. Okay, so yeah, those are the things basically. So it is used to control below base speed, and here the torque will be constant, and the field control methods, it is used to control above base speed, and power will be constant. Okay, constant power operation. So these are the basically key points. I hope you understand this basic point. Okay, so here this is how we convert using field, this is how we control using field diverter control. That's how the current is changed. And here this is the tapped control where the number of turns have changed. Okay, and series parallel already we have discussed, right? Series parallel should be not here, it should be on that place only. Yeah, series parallel is here, where we connect two windings either in series or in parallel. Accordingly the number of turns will basically change. Okay, now let's discuss about one more case where I am connecting the motors in series parallel. Okay, that I guess we will discuss later on. Let me discuss now only. Let me discuss, as I think that is not discussed later on, right? Okay, here, yeah, actually it is there. It is there. So what we can do, yeah, we can take this slide here. So what if I connect two motors in series and parallel? What will happen then? So basically, let's say I have a like, let's study the special case of series and parallel connection let us study the special case of series and parallel combination of DC series motor. Okay, so uh, basically what we understand is what is the relationship. So if I have two motors, you try it out by yourself, pause the video and try it out by yourself. If I have two motors, right, if let's say these two motors, both of them are series motors only, in one case they are connected in series and in the other case they are connected in parallel. In the other case they are connected in parallel. So now can you tell me what will happen to the speed? What will happen to the speed in both these cases? So how can I define the equation of speed? So one thing I know, this is the case 1, this is the case 2. So one thing I know is that like two fundamental equations I always know, right? What are the two fundamental equations? The two fundamental equations is basically EB is proportional to phi n and my torque is proportional to phi Ia. Okay, torque is proportional to phi Ia. Also, what is my EB proportional to? So EB, right? EB is equals to V minus IARA, right? And if I assume that okay, IARA plus RSC, if I assume my IA to be very low, if I assume my IA to be very low, then I can say that EB is proportional to V. Okay, so assumption is IA very low. IA very low. Okay, if I assume my IA to be very low, if the IA is very low, then EB is proportional to V. So my speed, right? Speed is basically, if I say speed is proportional to EB by phi, and what is phi proportional to? Phi is proportional to the armature current only, right? So it is proportional to EB is proportional to V by I. So whatever is the overall voltage across the equivalent and whatever is the current across the equivalent, that is what my speed is proportional to. Correct? So now if I connect two series motors in series connection, what will happen? So here, right, what is torque? Torque is proportional to Ia whole square, right? It only depends on Ia because flux is proportional to current. So in this case, the torque does not change. So in case 1, torque will remain same as same as same current Ia flows through the load, flows through both the motors, right? So torque will be same, but what about the speed? If I see speed, right, here the voltage is V by 2. If I assume them to be like almost similar or every parameter is same for both the motors, this voltage drop will be V by 2. If I am applying V voltage and I am supplying I current, then this voltage will be V by 2, this voltage will be V by 2. So same current II is flowing. So it is rated voltage and rated current, right? So V by 2 is there. So my speed, right? Speed is proportional to V by I. So I is same, but V has changed to V by 2. So basically N dash will be N by 2 because your speed is directly proportional to the voltage. So speed will be halved. So speed of each motor will be halved. Now in the case 2, if I apply the same rated voltage and I am supplying the same rated current, what will happen? In the case 2, if I am applying the same rated voltage and same rated current is passing by, so this current will be I by 2 and this current will be I by 2 because they are identical, so they will provide equal impedance. So both of them I by 2 current will flow through them. Okay. So what I can comment is that now what will happen to the torque? So torque is proportional to Ia square. So torque current has been halved. So torque T dash, right, will be T by 4, right, because T1 by T2 will be equals to Ia1 divided by Ia2. So in this case Ia2 is basically Ia1 divided by 2, right, because current has been halved. So this whole square, right, this whole square. So ultimately your T2 will be T1 divided by 4 because Ia2 is Ia1 divided by 2. Okay. Now torque will be 1 by 4. What about the speed? So speed, again I have discussed that it is proportional to V by I. So voltage rating is same, but the current has half now. So basically N1 divided by N2 will be V1 divided by I1 into I2 divided by V2. So this will be basically N2 will be equals to N1 into V1 divided by V2. V1 and V2 are same, so that will cancel out. It will be I2, I1 divided by I2. I1 is I only, I2 is I by 2. So the speed is twice the previous speed. So N2 will be 2N, right? So speed becomes double. If I connect two series motors in parallel, speed will double, torque will be quarter, like 1/4. Torque will be 1/4. And if I connect two DC series motor in series with each other, torque will remain same because the current is same, but voltage is halved, so the speed will be halved. Okay. So I hope you have understood this basic point. How do I connect two series DC motors? Okay. So series connection. So how multiple DC series motors can be used in traction vehicles. So if I, like initially, right, initially what is happening, initially the torque is same. So what I can do is I can connect two DC series motor initially at startup to provide, like both of them overall, like the torque provided by one series motor is T because torque is same, and torque provided by this series motor is also T. So overall they will provide 2T amount of torque. So I can connect two DC series motor in series with each other. So both of them will assist at startup because at startup I need high starting torque because initially there will be inertia. So two identical DC series motor are connected in series across the supply voltage. The motor effectively receives half the rated voltage. Hence the starting with reduced speed, but the torque is same. So both of them contribute additional torque, right? So because at starting I need high torque, not high speed. Okay. So when we want to accelerate, let's say I want to accelerate, right, I want my speed to go beyond my rated speed, so parallel connection will be used. So I can connect two motors in parallel. Once the vehicle accelerates, the same motor can be switched to a parallel configuration. Each motor now receives full supply voltage, leading to increased speed because the current has been halved. If the current has been halved, then the speed doubles, right? That's the reasoning. So that's why these kind of control can be done. So further we can use, of course, field control to, of course, change the flux and make it series parallel, or using diverters control the field flux to control the speed, that already we have discussed, right? So this is also another way with which we can control our DC series motor speed. So questions will be very simple, don't worry I think. Okay, so let's do a few questions and from there we will see. So a DC series motor operates at 1000 rpm. So DC series motor is operating at 1000 rpm while drawing a current. It draws a current IA equals to IL, that is 20 amperes, from 200 volt supply. So VT is 200 volts. The armature and series field resistance. The armature and series field resistance. So armature resistance RA is 0.5 ohms and series field resistance RAC is 0.2 ohms. If the motor continues to draw 20 amperes of current, so the motor is drawing 20 amperes of current only in the second case, but the field winding is now shunted with a 0.2 ohm resistor. So this is my field winding which has a resistor of 0.2 ohms, and I have shunted my field winding with a diverter resistance of 0.2 ohm. So this is the R diverter. Determine the new speed. So they are asking N dash in RPM. Assume that the flux produced by the field winding at 10 ampere is 70% of the flux at 20 amperes. Okay. Okay. So they are telling me now what will be the current through the series field winding. Now one more thing you have to understand is, although we assume that the flux, right, linearly decreases with current, but actually the BH curve is somewhat like this. Correct? This is the BH curve. So maybe if there is some linear decrease in current, that is the magnetizing force, maybe the decrease in the flux, that is the magnetic flux density, is not linear. So if it is not linear, maybe it has to have some empirical formula. So what they're telling me, in the first case, what was the current through the field winding? So in the first case, the current through the field winding IF was 20 amperes only, because nothing was there, it was a series connection. In the second case, as I have a parallel path, so here 20 amperes of current is flowing, right? So how much current will flow through this path and this path? Both of them are providing same resistance. So current through this path will be 10 amperes. Right, both of them provide the same resistance, so current through this path will be 10 amperes only. Okay, current through this path will be 10 amperes only. Okay, so current through this path is 10 amperes. So now what I can do, they are telling me that when the current through the field winding is 10 amperes, it is 70% of the flux when it was 20 amperes. So if IF was, let's say, 20 amperes, then the flux, let's say, was equals to 5F. Then in this case, when my IF is 10 amperes, IF dash is 10 amperes, then my phi dash will be 0.7 of the previous flux, that is 5F. So flux has been reduced to 70%, not overall 50%, because current has reduced by 50%, but flux has not reduced by 50% because this curve is not linear. Okay. Now, what are they asking? They are asking the new speed. So what is the speed formula? Speed is proportional to back EMF upon the flux. What is my back EMF? So it is proportional to VT minus IA RA plus RAC divided by flux, right? So flux has reduced to 70%. So I can do the ratio N1 divided by N2 will be equals to, VT is same, VT is 200 volts only, 200 minus IA. IA current, initially IA current was 20 amperes, and next case also it is 20 amperes only, they are not changing the IA current. So 20 into RA plus RAC. So RA is 0.5 ohms plus RAC. RAC is point ohms. Okay, divided by of course the flux. Initially let's assume the flux was 5. Okay, now let's come to the second case. In the second case, this voltage equation will be coming at the denominator. So in the second case, again this Vt will be same 200, Ia will be same 20, but this time Ra will be same 0.5, but Ra will be same 0.5, but RAC now two things are in parallel. So point 2 parallel point 2, point 1, it will be point 1, point 1. So this will be plus point 1, although it won't make much of a difference. And what will happen to the numerator? Numerator will be 0.7 times flux, because the flux has reduced to 70%, right? So flux produced will be 70% of the previous flux. So from here, what is the initial speed? Initial speed, they have told me it is 1000 rpm. It is 1000 rpm. So 1000 divided by n2, this will be 0.7. 20 into 0.7 plus 200, so 186. Divide by flux into, look, see, flux will get cancelled ultimately here, into 0.7 will be there, divided by 20 into 0.6 plus 200, so this will be 188. Okay, so 188 into 186 into 0.7, so this will be 0.69, this inverse into 1000, so the speed becomes 1443.93. so the speed n2 is 1443.93 rpm. Okay, so this will be the speed in the new case. So I hope you have understood how to tackle these kind of questions. Let's solve the next one. A DC series fan motor draws an armature current of 60 ampere while running steadily at 2000 rpm. Okay, so it draws a current of 60 ampere, and remember it is a 4-pole machine while running steadily at 2000 rpm, while the supply voltage Vt is 220 volts. The motor's 4 field coils are reconnected into 2 parallel branches. So the motor has 4 field coils. So these are the 4 field coils: 1 coil, 2 coil, 3 coil, 4 coil. So each of them will have turn n by 4, n by 4, n by 4, n by 4, and the resistance also will be RSC by 4. Overall resistance, if it is RAC, so this will be RAC by 4, or okay, let me write, yeah, it will be RAC by 4, pardon my handwriting, RAC by 4. Now they're telling me that reconnected into 2 parallel branches, each containing 2 coils in series. So now they are reconnected into 2 parallel branches. So I have 2 coils each in each branch in series. So this will be coil 1, coil 2, this will be coil 1, coil 2. So overall here, what will be the number of turns? Here the number of turns will be n by 2, and what will be the overall armature, sorry, series field winding resistance, RAC by 2, and here also same thing, n by 2, RAC by 2. So this is the equivalent combination. Okay, and overall resistance will be RAC by 4 now. Okay, but it does not matter, only this much matters. Now assuming that the magnetic flux is directly proportional to the excitation current, so flux is linearly proportional to IF. This time it is not following that saturation graph. Excitation current and the load torque varies with square of speed. So my load, they have given me this information that the load torque, they have given me this information that the load torque varies with square of speed. Okay, determine the motor's new speed and armature current. So initially this was the connection. For that it will have some current and some speed. Now they are asking in the new connection what will be the speed and the current. Okay. Okay. So what will be the changes in the flux? So initially, so they are telling me that load is not changed. So if load is not changed, right, it will draw same amount of current, that is 60 amperes. So let's assume that initially it is drawing IA amount of current. So whole of this IA current is flowing through all of the coils. So how much MMF will they produce? MMF produced will be N into IA. Okay, got it. In this case, what will be the MMF produce? So this will produce here, right, IA by 2 current will flow. Here also IA by 2 current will flow. So here the MMF produce will be number of turns in each coil into the current in each coil. As there are two of this combination, so I have to multiply by 2, right? So this will be N into IA divided by 2. So the MMF has been halved, so the flux also will be halved. So phi 1 divided by phi 2 is basically 2 divided by 1, because the MMF has been halved, flux also will be halved, because flux is equals to MMF upon reluctance. Okay, so yeah, I hope you have understood this basic point. Now what to do? Each containing two coils in series. Okay, so the flux has been halved, this is established. Now they are asking what is the new speed. So what is speed dependent on? So speed is roughly dependent, speed is dependent on EB divided by flux, right? So assumption is EB is what, VT minus IA RA. Now here in the question actually they have not mentioned what is the armature resistance, right? All those things have not been mentioned. So roughly I will say that it is roughly basically VT divided by flux. So the numerator is constant, it only depends on the flux. So flux has been halved, so speed will double. So N1 divided by N2 will be phi 2 divided by phi 1. So N2 will be equals to 2 into N1. So you will say that your N2 will be equals to 4000 RPM, and unfortunately you will be wrong. So whatever have been done in this particular page, right, is wrong. Why? Because I assumed my IA to be constant, but actually IA also will change, because I know my torque is a function of speed. The load torque is a function of speed, right? They have told me that load torque varies speed square. So if speed is changing, then torque also will change, hence the current also will change, and hence all these three are interrelated, right? So simply I cannot do it. Okay, so that is the most important portion that you have to understand. So but whatever we have discussed here, this is fixed. So your EB will be fixed because they have not mentioned about the drop. So one thing I can comment, that EB is equals to VT minus IA into RA plus RAC. They have told me that, they have not told me about RA and RAC, right? So I will assume it to be equals to VT. So I can say that your EB is constant, and EB is equals to what? EB is proportional to flux into speed. So your product of flux and speed both are constant. That is certain. Again, how will the flux change now? So again, right, this is incorrect, because previously I was simply cancelling out the IA1 and IA2. But here, right, what is actually happening? Previously I had this 4 coils, and initially the current that was flowing was IA1, right, and this turn was N by 4, this was N by 4, this was N by 4, this was N by 4. Okay, and here what was the MMF? So MMF in the first case is equals to n by 4 into IA1, and I have 4 coils in series, so it will be multiplied by 4. Okay. Now in the second case, I have n by 2, sorry, n by 4, n by 4 coils connected in series, and this combination is connected in parallel. But this time remember the current has changed. It is not IA1 anymore, it is IA2. So here, right, the current will be IA2 divided by 2. Here also the current will be IA2 divided by 2. So what will be the MMF in the case 2? MMF in the case 2, it will be n by 4 into 2 into IA2 by 2 into 2, because these two are connected in series, right? And additionally I have to multiply another 2 because this whole combination is connected in parallel. So another 2 I have to multiply because this whole combination is connected in parallel. So this will be basically n n by n into IA2 divided by 2. So from here I can directly say what will be the flux change, right? So the flux change I can say phi 2 by phi 1, as it is proportional to MMF, it will be MMF 2 upon MMF 1. So this will be equals to n into IA2 divided by 2 divided by n into IA1, right? In the first case it was simply n into IA1. So ultimately this comes out to be IA2 divided by 2 IA1. Okay. Now what is the other information? This is the information, right, that the flux, product of flux into speed will be constant. So EB1 divided by EB2 will be equals to phi 1 into N1 divided by phi 2 into N2 will be equals to phi 1 into N1 . So phi 1 into N1, right, phi 1 into N1. So phi 1 into N1, phi 1 into N1. So I can say here that phi 1, basically phi 2 by phi 1 is IA2 by I1. So phi 1 by phi 2 will be IA1 divided by IA2 into N1 divided by N2. So N1 divided by N2 also I don't know. Now what more information I know, that they have told me that speed and torque varies in the whole square. So what is the other thing? So my torque is speed whole square, it varies. Also my torque varies flux into IA. So this is also another relationship, right? So torque T1 divided by T2 will be phi 1 divided by, now this is 1, this is constant, this is 1, right? So because EB1 and EB2 are same, so EB1 and EB2 are same, so N1 divided by N2 is simply equals to IA2 divided by two IA1. Okay, so T1 divided by T2 will be phi 1 divided by phi 2 into IA1 divided by IA2. Okay, and it is also proportional to speed whole square. So this is simply equals to N1 divided by N2 whole square. That is given in the question. Torque is proportional to the speed whole square. That is given in the question, so I can use that information. So N1 divided by N2 whole square, this is the value, right? So simply this is what my N1 divided by N2 is. So what is phi 1 divided by phi 2? Phi 1 divided by phi 2 is this, opposite. So simply here this will be phi 1 divided by phi 2, right? So it will be 2 Ia1 divided by Ia2 into Ia1 divided by Ia2, and it is n1 divided by n2 whole square, and n1 divided by n2 whole square is this value. Okay, n1 divided by n2 whole square is this value. Ia2 divided by 2 Ia1 whole square. So from here we get a very peculiar, because Ia1 is given to me, initial armature current is given to me, that is 60 amperes. Okay, Ia1 is given to me, that is 60 amperes. So here from this equation what I can say is Ia2 raised to power 4 will be equals to 8 into Ia1 raised to power 4, right? So Ia2 will be equals to 8 raised to power 1 by 4 into Ia. Okay, so from here am I doing this absolutely correct? That is what I want to see. So phi 1 by phi 2, phi 1 by phi 2 will be, yeah, it will be twice, yes, 2 will be there, 8 will be there, yes, it is correct, 2 will be there, 8 will be there, yes, and 1 divided by n2 whole square, that is the equation, that is what they told me, right? Determine the motor's new speed and armature current reconnected into parallel branches, yes, it is correct. Okay, so what will be the new current? So the new current will be Ia1 is 60, so if I just take the 8 raised to power 0.25 into 60, so new current will be 100.9. okay, that will be the value of the new current. Okay, 100.9 amperes. What about the new speed? So new speed is this equation, right? So it will be n2 will be equals to n1, that is 1000 rpm, 2000 rpm, 2000 rpm into 2 into Ia1, that is 60, divided by Ia2, that is 100.9. so this comes out to be 2000 2300.78, so 2378 0.414 rpm. Okay, so this will be the speed basically, this will be the speed basically. So this will be the answer, speed and the current, this will be the answer. Let's now solve the next question. So in the next question, what have they told? A 4-pole DC series fan motor, it is operating in 600 rpm. So it's a 4-pole machine, it is operating in 600 rpm and drawing a supply Vt of 250 volts, drawing a line current of I equals to 20 amperes with all the field coils connected in series if it is reconfigured. Okay, oh, it's the same question only. Okay, it's the same question basically, like this you can do, right? It's the same question basically here, right? The difference is here the flux is directly proportional to armature current and the load torque varies. Okay, same question, it's the same question. Okay, so you should be able to do it, I will not do it, it's the same question. This is the homework for you. Okay, so the solution is basically provided over here, you can go through. Finally the answer will come out to be, yeah, this will be the current and this will be the speed. Okay, so I hope you have tried it out. So now let's discuss about braking of DC motor. So of course, if your motor is rotating and any vehicle is rotating, right, you have some mechanism to brake it, because suddenly some person will come in front of the car, you have to brake it, right? You have to stop the machine at that moment. How do we brake it? So there are many ways with which we can brake, right? So there is mechanical and electrical. So we will study electrical, why mechanical is not preferred, we will study about that as well. So mechanical braking, so braking in DC motor refers to the controlled deceleration of the motor by reducing or reversing the developed torque to bring the motor to rest more quickly, okay, and safely than simply allowing it to coast. So if I don't press the brake button, the machine, the vehicle will just go ahead and it will just uh, I mean, there will be accident with the person, right, that is in front of the motor. So we don't want that. So that's why we want to brake the motor at that instant of time only. So to do that, there are few mechanisms. So there is one mechanical braking and electrical braking. So mechanical braking involves physical contact like brake shoe or friction discs to stop the motor brake. So the vehicle is rotating like this, right, in circular region. So what I'll do, I will have few shoes that will connect here, so that will restrain the clockwise movement of the motion so that it stops. But there is friction between the pole shoe and whatever like bearings are connected over here. Due to that, wiring and tearing of mechanical parts will happen. So due to that, we have to do maintenance of the machine. That's why you see, if you buy a bike or a car, right, regularly you have to go to the service and do servicing of the machine, do maintenance of the car and the bike, because there are mechanical parts and because there is so much friction, wiring and tearing. Due to that reason, the parts get damaged, so we have to replace those parts or service those parts. Okay, so that is what my mechanical braking is. So what are the disadvantages? Certain braking can be jerky or unsafe for sensitive machinery. So if the pole shoe is suddenly here, right, and it is trying to make the machine go to rest, so it can be jerky. So if you sit in bike or car, right, suddenly if your father or whoever is driving the car, suddenly if he presses the brake like a paddle, what happens? Suddenly you feel a jerk, right? So that is kind of a mechanical brake. Okay, that is not smooth enough. Then we have high wear and tear, as I mentioned, and it is not that energy efficient because huge kinetic energy is lost as a form of heat, because whenever two things are in contact, sparking happens, heat energy is lost, so energy is lost. So due to all this reason, we do not prefer mechanical energy, we prefer electrical braking. Okay, so electrical braking is smoother, more efficient, lower maintenance compared to mechanical braking. It works by removing or opposing the stored kinetic energy of the rotating parts using electrical means. Instead of the energy getting lost using heat energy, kinetic energy, of course, what is happening initially, if your machine is rotating, so what is the energy? Initial energy half mv square kinetic energy across the machine, right? Now you want to bring the machine to rest. So what will be the Ke final? This is the Ke initial kinetic energy, and Ke final is half like 0, right? Because here the velocity is 0. So I want to, of course, I have to bring the machine to rest. So how will I do it? So I have to make whatever energy the machine has to make it 0. So there are many ways with which we can change this energy. So one way is, if I use heat energy, like whatever energy was there, all of that is lost in heat energy. That is not a good way to, just waste the energy, right? So what we will do, whatever energy we have, whatever kinetic energy we had, we will try to lose it through electrical means like resistance. Okay, I square RT, that is also a kind of heat energy, but that is much more smoother than this one. Okay, and we will learn few other methods as well, through which maybe there will not be much energy loss. We will discuss about that. Okay, so electrical braking is used to decelerate or stop a motor by electrical means rather than relying solely on mechanical friction. So in actual scenario, both electrical and mechanical brakes are used in conjunction. So both are used together. Okay, in actual scenario, it is especially used in systems where controlled slowing or frequent stopping is required, such as cranes, hoist, elevators. All these cases, electrical braking will be used. Unlike mechanical braking, electrical braking methods recover or dissipate the motor's kinetic energy. Okay, they do not lose it totally in heat energy. Some of the energy can be recovered, so which will overall improve the energy efficiency and reduce the mechanical wear. So here there are no mechanical parts, so basically maintenance will be lower. So like the easiest way to stop a machine, you just disconnect the motor, okay, while running. But will it totally stop? No, it will not instantly stop, because the machine if this is rotating, right, this is rotating, and if I just turn off the supply, what will happen? Current will be zero, but still this machine has some inertia, right? Due to that, still it will move ahead, just like if I turn off the engine of a car, and if the car is moving, it's not like it will stop at that instant, it will still move ahead few meters, because the car has some inertia, and the tires are still rotating, okay. Due to that, the machine, the car will still move ahead. So that is the thing over here. So let's discuss the first one. First method of braking, first one is known as the plugging, okay. So mainly we will be discussing about DC shunt machine only. In plugging, what we do is, I know that this is the state where my machine is running, okay, and I have to stop my machine. How can I stop my machine? So we know, so I have to decelerate. So how can I decelerate? My torque is what? Torque is phi into Ia. So I can decelerate mainly for braking, right? For braking, I have to deaccelerate. For braking, I have to deaccelerate. How can I deaccelerate? If I reduce my torque, right? Or if the torque is in the opposite direction, then what will happen? Then the machine will simply deaccelerate, right? Because there will be negative acceleration, correct? So torque needs to be negative. How can I make it negative? If either you make the flux negative or the current negative. So previously whatever was the direction, if now the direction I change it, so torque will be negative, okay. Torque will be negative, okay. So now what I will do is, I will make the torque negative. I will make the torque negative. If I make the torque negative, so either you change the flux direction or you change the current direction, right? Both of them will make, either, like, I cannot do both. I cannot change both, right? Either you make one of them reverse, then the basically then the torque will be negative. So I will get a deacceleration, okay. So this method is known as plugging, where plugging either what we do, either reverse the field terminals, either reverse the field terminals or the armature terminals. Then what will happen? Then basically the connection diagram, I can draw the connection diagram, then the torque will be reversed. So torque direction reverses, so there will be deacceleration, and due to that basically the motor stops, okay. Now isn't energy lost here? Is energy lost here? So energy is actually lost, we'll see. So first one is, you have the option, which one do you want to reverse? Do you want to reverse the field terminals or the armature? So most of you guys, I guess, will say I want to reverse the field terminals, but changing the field terminals will have a bit of problem. So one thing I know, in case of a shunt machine, that the number of turns of a shunt motor, shunt winding, is much higher, right, than the number of turns of armature winding, because we have learned the property that the number of turns of a shunt winding is very high, because the current is very low. So mmf I need to mmf I need to produce. So due to that, the number of turns in the shunt winding will be very high, right. So if the number of turns in the shunt winding is very high, I know the formula for inductance, right, is proportional to the number of turns, correct? So the shunt inductance will be much higher than the armature inductance. Now why is this important? Because ultimately, how will I change the direction of flux? How will I change it? So what I will do is, initially, if say, let's say this is my field winding and some IF current is flowing, okay, then if the direction of the current is changed, that is how the direction of the flux will be changed. So this will be IF now, okay. So basically what is happening, so this was at, let's say, t equals to 0 minus, this is at t equals to 0 plus. So at delta t amount of time, the current is changing delta I from plus IF to minus IF. So what is the change in current? Minus IF minus of IF, so it is minus of 2IF, right? So you know this is an inductive circuit, so the developed voltage VL will be equals to L shunt into delta IL upon delta T. So it will be L shunt into minus of 2IF divided by delta T. So in case of a shunt machine, the L shunt already I have discussed is very high, so the reactance voltage also will be very high, right? And we actually don't want this, right? There will be reactance voltage, there can be sparking due to the reactance voltage, insulation failure also can be there. So all these things we actually don't want. Okay, there can be insulation failure and all those things. So that's why what we will do, we will, hence we avoid swapping field terminals, we swap basically the armature terminals. Or what we do is, maybe the armature is not accessible, so what we'll do, we'll swap both the supply and the field terminals. So the current through the field terminals will be same, but the current through the armature will change. So here is what we'll do. So here, initial, this is the state. Now when I am trying to break it, what I will do, I will change the field terminal connections. Also I'll change the supply terminal connections. So this will be plus now and this will be minus. Okay, that's it. So the current will be somewhat like this, and if current is somewhat like this, then what happens, the IA current direction previously was downwards, now it is upwards. So IA current direction has changed. Is the field winding current direction has changed? No. So this current will come here, still it is going like this from left to right. So in the previous case as well, current was going from left to right. So this current direction has not changed, IA direction has changed, so the torque will change. One more thing, one more key point is that, remember, the motor is still rotating in the same, let's say previously if it was rotating in the clockwise direction, now also it will rotate in the same clockwise direction. So what is my EB? So EB is proportional to flux into, EB is proportional to flux into speed. So speed, right? Yeah, speed is reducing, but direction of rotation is still same. So let's say this is rotating, right? So speed is reducing, so it is still moving in the clockwise direction, but now it will move slower. So direction of rotation is same. So previously if this was positive, this will still be positive only. And flux direction also, if you see, I have not changed because automatically they have been swapped. So flux is also greater than 0. So EB is still positive. So if I draw the circuit in the case 1 and case 2, so this is the motor, this is the back EMF while the motor is operating normally. And here was the previously supply VT RA. Okay. Now what I can do is in the second case, EB is not changing, the direction of EB will not change because it is still positive, but I am swiping the field terminals and the supply terminals are also being swapped. Okay, so I can say that my now what is the armature current? So here what was the armature current? So here the armature current IA was equals to VT minus EB divided by RA. And here, right, yes, speed is reducing. For a second, if I just assume at that same instant, because at that same instant speed will not instantly go to 0, still it will be the same, almost similar speed only. Here what is the armature current? Here IA dash. Here, right, if you apply KVL, right, you will see that your value is coming out to be IA dash is coming out to be minus of VT plus EB. So this will not be minus, plus Vt by Eb, because this is the direction of Ia, Vt plus Eb divided by Ra. So if you observe here that basically what do you observe, that the Ia dash, right, magnitude of Ia dash, direction, I'm not talking about the direction, is much greater than magnitude of the previous current. So armature current is hugely increased, that can damage the armature. Okay, so to mitigate that, basically what we will do, we will basically simply add a external resistance. We will simply add a external resistance and that's it. Okay, if I add external resistance, so this R external will come in here, that will further help in reduction of the armature current. Okay, so that is what we will do extra here, nothing else. So I hope you have understood this basic point. So yeah, whatever we have discussed, same thing is written. Field winding will have higher inductance, so LF will be higher greater than LA. So inductance resists sudden change. So we will reverse the armature terminals, not the field terminals. And again, when terminals are reversed, armature current will shoot up. I have discussed why it will shoot up. So we will add a external resistance to negate the effect of the extra current. Okay, so what is the braking torque that is getting produced, or what is the plugging torque? So the plugging torque, right, what is my torque equals to? So torque is equals to proportional to phi into Ia. Again, as I am not doing anything with the flux, right, so flux is again constant, I'm not changing anything with the flux. So because the flux direction also is also same, flux is constant, I am changing the armature current, right? And armature current is what? Armature current is this value, right, while there is a brake on. So your plugging torque will be kt into phi. Flux does not change, but this will change. This will be v plus eb divided by whatever was the previous back emf divided by ra plus r external. Okay, so this is the equation for the plugging torque. So this is the theory that we need for the plugging torque. Okay, so now let's discuss about the other kind of torque, that is dynamic or rheostatic braking. Okay, so let's discuss, like, of course you will not forever apply this plugging torque. After a certain point the plugging should be stopped. Okay, because then mechanical braking will be used. Generally that is what we do. Have they mentioned it? No. So one key point, yeah, important considerations: plugging torque is high and acts in the same direction as the load torque, producing braking effect. Energy consumption is high. Why? Because the current, right, previously the current that it is taking from the supply has increased very much, right? And what is the energy energy consumption? It is Vt into I, right? Ia has increased, right? If you see, Ia has increased hugely. So Vt into Ia or Vt into I also will be increased hugely, right? So that's why the energy consumption will be very, very high. So where is it dissipated? It is dissipated in the armature and the external resistance, because Ia is very high. So again the armature loss, Ia square Ra plus Ia square into R external. So all these will be lost in the heat energy. If supply is not disconnected, once the speed is reached 0, the motor will start rotating in reverse. So you must disconnect the supply before the speed reaches 0, because now remember the torque is acting in the opposite direction. If you keep on forcing the torque in the opposite direction, the motor will go backwards, right? You don't want that. Okay, so hence disconnecting from the hence disconnection must occur near 0 using contactor or sensors. So what we do is we use plugging till 70%, till speed reaches 30% of rated speed. After that what we will do? After that we will simply use mechanical brakings. So that's why I said to you that we will use combination of electrical and mechanical braking. After that we will use mechanical brakes. Okay, so this is what they are talking about. Okay, after it reaches 30% we will use mechanical brakes. Okay, advantage is provide strong and immediate braking, so huge amount of reverse torque it will provide. Simple implementation with minimal circuit change, used in systems requiring emergency backup braking, braking such as elevators and hoist. Okay, so yeah, I hope you have understood this basic point. Now let's study about dynamic braking. So in dynamic braking what we do is, instead of like just disconnecting the supply, if you disconnect the supply across a motor, what will happen? The machine slowly will deaccelerate, because there will not be any flux as well, so there will not be any torque. So torque is 0 now. So if torque is 0, so automatically the machine will deaccelerate slowly. Here the torque was negative, so I was providing deceleration. Here I am not providing neither acceleration neither deceleration. So slowly, due to air friction and drag, machine will come to rest. But what if one thing I do, after disconnecting the armatures, what I do, I turn on the field windings. The field windings still will pass some current. I connect this armature terminals to an R brake external resistance. So what will happen? This has some induced developed voltage EB. So there will be some current flowing through it, and the current will be in opposite direction. So previously, if the current was in this direction, now if I draw the equivalent circuit will be somewhat like this. So the current will be in this direction, right? This is R brake. This is EB. This is RA. So I can directly say that what will be the IA this time? IA is in this direction. It will go out of the supply terminals, I mean the armature terminals. So IA will be E brake by RA plus R brake, right? So IA is in opposite direction. Previously IA was downwards, so now IA is in opposite direction. So of course the torque also will be negative, so there will be deceleration. As the torque is negative, there will be deacceleration. There will be deacceleration. So now I can do whatever, like if the R brake is lower, so IA current will be very high, so braking intensity will be higher. If I make the R brake to be higher, then the IA current will be lower, so the braking intensity will be lower, right? So braking intensity can be increased by using lower braking resistance, or it can be decreased by higher braking resistance. So ensuring high field current to maintain strong excitation. So of course field current should not be changed, because my EB, right, depends on what? Flux and the speed, correct? So at t equals to 0, speed is same, field current is same, so EB value will be still same. But as I am providing some deacceleration, what will happen? The speed will reduce, hence the EB also will reduce, hence the rate at which deceleration was happening, that also will reduce, okay, but still it will be there, okay. So advantage, it can also be combined with the electronic control circuit to regulate the deceleration rate. How fast or slow I want to deaccelerate, that also can be controlled using electronic circuitry. No energy feedback to the supply is required, okay. So there is no energy feedback to the supply, making it suitable for isolated or stand-alone systems. Simple to implement and safe, as the motor supply is disconnected. No reversal of torque is required. So automatically the torque is getting reversed. I don't need to change the supply terminals, and huge kinetic energy is also not lost, right? Yes, energy is lost, but it is not as high as plugging. So here another advantage is less energy is lost than in the case of plugging. So in the case of plugging, there was more energy lost. In case of this, there is less energy lost, okay. Now if you like, what are the disadvantages? So the disadvantages is all energy is lost as heat in braking resistance. So all of the energy will be lost in heat. Braking effectiveness depends on motor speed. So if the motor speed is very high, then EB value will be very high, right? So basically it depends on the value of EB, and EB in turn depends on the value of speed. So if the motor speed is very high, then EB will be very high, then this IA in the reverse direction current also will be very high. So the deaccelerating torque also will be very high. If the motor speed is low, then EB value is low. If EB value is low, then the current also will be low, then the deaccelerating torque also will be lower, okay. So these are the things basically that you have to keep in mind. Now you might have a doubt, sir, what if you disconnect both the field winding and the supply? If you disconnect both the field winding and the armature winding, basically your EB will be 0, right? If EB is 0, there is no deaccelerating torque, simply the torque is 0, so it will also slow down. It is just like disconnecting the whole supply from the motor. the motor will stop, but at what cost? You cannot instantly stop it. It will stop after it moves forward few meters, right? So that can cause accidents and damage. Okay, so yeah, don't disconnect the whole supply directly. And next kind of braking is known as the regenerative braking. In regenerative braking, we use the concept of over excitation. Okay, so in regenerative braking, the motor operates as generator during braking. This occurs when the load drives the motor faster than its no load speeds. So if I am operating the motor, let's say n operating is higher than the rated speed n rated, then what will happen? Then my EB will be higher than the V rated, EB rated, and EB rated, let's say, is almost very near to the terminal voltage. So EB will be higher than V. Then what will happen? Basically, then what will happen is that if I see here, if I draw the circuit, this is my EB and this is my supply, it VT or VS, correct? This is my RA, and I am saying that EB is higher than the supply voltage. So what will be the direction of current? Direction of current will be in this direction now. Why? Because which point is higher potential? EB point, right? EB is higher. So of course current will flow from positive to negative. So sorry, higher potential to lower potential. So the direction of the current will reverse. Hence, it will work as a generator now. But it happens when? It happens only when the motor speed exceeds a rated speed, only when the EB is higher than VT. Okay, it will not always work. So here no energy is lost, but I am delivering energy to the supply. Okay, so as a result, the current direction reverses. So the power also flows back to the source. Also the torque direction reverses. Hence, of course, there will be deceleration. What will happen is in steady state again the speed will try to reduce. Okay, so when the motor speed increases, let's say if I am going downhill, right? I am going downhill. So what happens in downhill? The speed increases very fast because there is an extra additional accelerating constant. So if you remember, I have a wedge here, right, and I have a ball here, and if I just leave this ball in this top position, what will happen? It will experience a gravitational force. So G is here, but it will experience a force here along this direction. If I assume this angle to be theta, so so basically this angle is also theta. If this is theta, this angle should also be, hold on a second, yeah, this angle should also be theta. Yeah, this angle should also be theta. So it will experience a force of G cos theta, right, in this direction. So not G, yeah, experience acceleration in this direction, right, force of mg cos theta. So of course that is the problem. Am I correct here? I'm just checking. Okay, I have also forgotten all these concepts. This is theta, so this will be theta. So okay, and this is straight line and this is straight line. So yeah, this will be theta. Okay, this will not be theta. Sorry. So this will be 90 minus theta. That is what I was thinking. This will be 90 minus theta. Okay, so this will be sin theta. Okay, this will be G sin theta. So that is the case over here. I hope you have understood this basic point. So what else can I say? So basically, yeah, this will be G sin theta. So like what happens? It accelerates. So it may rotate at a higher speed than the rated speed, and due to that, what can happen? Our motor can supply back to the supply terminals. Okay, so the armature current IA reverses, the machine starts generating. The generated electrical energy is fed back to the supply system. Since IA reverses, the mechanical torque developed also opposes the direction of rotation, thus applying a braking effect. So automatically there will be inherent braking effect applied. Okay, so but of course it will not go to 0. Basically it will go to the rated speed. Okay, braking effect is there, but it is only when the case speed is higher than n rated. Braking effect will not be there when the speed is lower than the rated speed. Okay, so of course I cannot make my motor to stop at 0 speed. That is not possible in regenerative braking, but the advantage of regenerative braking is no energy is lost. Okay, so whatever energy is there, that is being delivered to the supply. So we are delivering. So what are the conditions? Supply voltage should be reduced. If I want regenerative braking, either you can increase the generated voltage or you can reduce the supply voltage. If you reduce the supply voltage, what happens? Again the current direction changes. That also can lead to regenerative braking. Then the power will be fed back to the supply, and the motor should be over excited, that is increased field excitation to make EB higher. So EB depends on either speed or N, right? So if you don't want to increase the speed, what you can do, you can increase the flux. If you increase the flux, your EB also increases. So in that manner as well, you can increase your machine back EMF. So that particular condition is known as over excited, because I am exciting the field winding more than the rated condition. Motor speed must be greater than no load speed, then that also will increase the AV value as discussed. Okay, so it is only feasible only feasible when the supply can accept the return power. So supply also has to accept it, right? So if you are sending some, like if you are learning something, let's say I am teaching something, but you should also have the capability to accept that whatever I am teaching, you should have the capability to understand that thing. If you don't have the capability to understand that, so whatever I will say, that will not make any difference, because you are not understanding anything. Okay, so that is the key point about regeneration. It is commonly used in electrical traction, where this regeneration is used. In DC series motion, regenerative braking is not as straightforward, since the torque may not reverse due to the may not reverse properly even if current does, because torque is proportional to Ia squared. So maybe we have to configure it according to a shunt machine for a DC series motor. If I want to use the regenerative braking in a DC series motor, I have to reconfigure it as a connection of DC shunt motor. Okay, these are the key points. So it is efficiency is much higher than plugging or dynamic braking, because no energy is lost. Whatever is lost, that is getting recovered in the supply, that is getting returned to the supply. Widely used in electrical vehicles, so whatever latest technology you see, widely used in that regenerative braking. Electrical trends, elevators, where energy recovered during braking can charge batteries or be reused by other systems. Okay, limitation: regenerative braking cannot be used to stop the motor completely. Only I can bring the motor to rated speed. Speed can be equals to N rated. I cannot bring the motor speed to 0. It is mainly used for protection against overspeed or for energy recovery during deacceleration. Okay, highly energy efficient, and these are the cons. Cons is the circuitry will become a bit complex if I am controlling few things. Okay, so you can go through and read over this, and these are the basically differences. So what are the energy utilization, what is the torque reversal, will torque reversal happen or not, efficiency, how much is the electrical efficiency, what applications are they used, does current get reversed, does supply will be connected or disconnected, all these parameters are there. So this is one short table for you to quickly go through the braking topic. Okay, so now what I want you to do is pause the video and try out these questions, and I will come back with the solutions of these three questions. This is the question and this is the question. So let's solve this question. A 400 volt DC shunt motor is delivering at rated load at an angular speed of 100 radian per second. So my VT is 400 volts and I'm delivering at 100 radian per second. 100 radian per second while drawing a current of 30 amperes. Okay, so it draws a current of 30 amperes. So that is what the current initially is. Okay, now, okay, actually this shunt resistance is also given, armature resistance is also given. So this current will be the line current 30 amperes. Actually, they should mention whether this is line current or not. By default, we will assume this to be the line current. Okay, so because the shunt resistance is also given, so we will be able to find out the field current. That's why here, right, if shunt resistance was not given, then there was no way for us to find the field current. Then we had to assume it to be armature current. You will see this will be roughly equals to armature current, but if no information is given about the field current, then you will assume this to be armature current. But if information is given about the shunt resistance, then this will be the line current only. So the circuit will be somewhat like this. Okay, circuit will be somewhat like this. Here I will have a armature resistance, then here I have the voltage to 400 volts, right? Armature resistance is 1 ohms and the shunt resistance is 200 ohms. So what is the field current? Field current will be 400 divided by 200, that is 2 amperes. So the armature current will be 28 amperes. Okay, so what will be the back EMF in this case? So what are they asking? So okay, what is the total voltage drop across the armature resistance during plugging? Okay, so we are using plugging, so what will be the total voltage drop across the armature resistance during plugging? So for that, right, what is the initial back EMF? EB, initial back EMF is basically VT 400 minus IARA 28 into 1, so this will be 372 volts, correct? Now if I am using plugging, what will happen? If I am using plugging, simply the armature terminals will be reversed, right? So if the armature terminals are reversed, then basically this will be connected here and this will be connected here. So if it is reversed, at that particular instant EB will still be EB only, it will not change. So if I redraw the circuit, this will be basically RSH, that is 200 ohms. This will be RA, that is 1 ohms. This will be the back EMF EB, and this will be connected here and this will be connected to the top, correct? So this is okay, this is my VT, which is 400 volts. So now I can simply apply what is the total voltage drop across the armature resistance. So what is the current? So drop will be current into the armature resistance. So what is the current now? IA dash. IA dash will be simply 400 plus EB divided by 1. So IARA will be IA dash into RA, because 1 is the RA only. That will be 400 plus EB. So it will be 772 volts. So are you able to see how huge of a drop this is? 772 volts. Okay, this is the drop across the armature resistance. And what is the current? Current is IA dash is simply 772 amperes, because the armature resistance is 1 ohms. What value of external resistance should be added in series with the armature to limit the armature current to 150% of its rated value during plugging? So initially, what was the armature current? Initially, the rated value, it was when it was delivering the rated load. Initially, the armature current was 28 amperes. So I want to limit the armature current to 150% of 28 amperes. So I want in the option B my IA dash to be 150% of 28. So this will be 3 by 2 into 28. Okay, this should be equals to basically VT plus EB divided by RA plus R external. So this will be basically RA is 1 plus R external will be equals to 14 into 3. So divide by 52, 14 into 3. So 14 into 3 is 52, sorry, not 52, 42. 42 and this will be 772. So if I divide these numbers, 772 divided by 42 minus 1, approximately R external comes out to be 17.38 ohms. Okay, this is my R external that I need to connect in series so that the so that the current is limited. Now the third part, what will be the resulting breaking torque? Okay, what will be the resulting breaking torque? So to understand what will be the resulting breaking torque, we have to understand what was the initial torque, right? So initially when plugging was not applied, initially my overall torque was what? Overall torque was TD was equals to TL. Okay, developed torque was equals to TL. What is developed torque? Developed torque is omega into sorry, this is developed torque, right? Now how do I find out the developed torque? I know this formula, EB into IA is equals to omega m into TD, right? Developed torque. So from here I will be able to find out what is my initial TD, that is EB by IA divided by omega m. So this is also equals to your load torque. Okay, so what is this value? So I know what is EB initially was 372 into IA initially was 28. IA initially was 28 and what is omega m? Omega m initially was 100 radian per second. So this will be 100 radian per second. Okay, so this is my load torque, right? In the second case, when plugging is there actually, so plugging, right? So what is the overall torque? So what is the overall torque that will be applied? Braking torque. So braking torque, now we'll have two things. Both the plugging torque will be there because it is in opposing nature, plus the load torque. Previously there were no brakes on, so previously my developed torque was opposite to the load torque and both were equal, hence there were no braking. Initially there was no braking, that's why this braking torque is overall 0 or the net torque. So in this case, as there is braking, due to reversal, of course there will be a torque developed due to plugging, but this load is still present there. It's not like I have removed my load is still there. So if load is still there, that will also provide its own torque. That will also still be present. Okay, that is the important portion to understand. Now what is the plugging torque? Plugging torque, right, is the developed torque due to the electromagnetic reaction between the current and voltage. So it is basically equals to, again the same thing, EB dash into IA dash. So EB dash is same as EB because I am talking about at that particular instant when just I have reversed the connection. So just at that moment, EB dash and EB will be same. So EB dash equals to EB just after reversing the connection. Okay, so this will be equals to EB into IA dash. Now current has changed. Current is now IA dash current is now 772. Okay, 772. So this will be 772, and so your plugging torque, right? It will be EB also divided by omega m. Also we have to do divide by speed basically. So speed just right at that particular instant, speed also will be omega m only. It will not change. Correct. So this will be basically divide by 100 only, and EB value is basically 372. So 372 into 772 divided by 100, and overall brake torque will be equals to T brake will be equals to this. So what I can do, 1 by omega will be constant, 372 into 772 plus load torque is this value, right? 372 into 28, 372 into 28. So basically it is 372 into 800 divided by 100. So it is 8 into 372. So 8 into 372, it is 2976 Newton meter. Now remember, this is without resistor. Okay, this is what we have derived. This is without resistor. Without R external. Now with R external, what will happen? With R external, basically your current, right? Current is simply 28%, 150% of the rated. So it is 42 amperes. So your IA dash is 150% of 28 amperes. So it will be 42 amperes. So what I can say is, now the plugging torque, right, will slightly be reduced. EB will still be, EB dash will still be equals to EB only, but the armature current, right, has reduced. So it will be EB into 42 150, right? 15 plus this, yes, 42 divided by 100. So now overall braking torque will be 1 by 100 into the previous value, that was EB2 into IA2. It was previously, it was taking 28, now it will take 372 also I can take outside. It will be 28 plus 42. Okay, so this will be equals to 70. So now 70 into 372 divided by 100, so it becomes 260.4. So with the resistor, of course, the torque will reduce. So it depends. So of course this will be your answer, right? Because of course you have added the resistor, then only you are calculating the torque, right? So I'm just showing you the significant difference on the braking torque. Of course there will be significant difference on the braking torque, but ultimately you do not want to damage your machine, right? Because armature current will be huge. Okay, so to nullify the effect of armature current that huge, so we have to connect the external resistance. There is drawback, the braking torque will reduce, so the speed, the rate at which the braking will happen will reduce, go down, but that's fine. Okay, there is a trade-off in everything. Okay, so let's now move on to the next one. A 15 kilowatt 240 volt 1500 rpm. Okay, so I will keep on writing. So P rated is equals to 15 kilowatt, the terminal voltage Vt is equals to 240 volts, speed is equals to 1500 rpm, current equals to 72, right? And they have provided only the armature resistance, so I'll assume this current to be the armature current only, because shunt field is not present. So neglect shunt field current, they have already mentioned, so I'll assume this to be the armature current. And the armature resistance is 0.3 ohms. The motor is brought to a stop using plugging. If the armature current is to be limited 1.2 times the rated value during braking, determine the external resistance to be added. So when it is operating, which is operating under rated condition. If it is operating under rated condition, so speed is rated, voltage is rated, current also will be rated. So I will be able to easily able to find out what is EB. EB will be Vt minus IaRa. So Vt is 240 volts, 240 minus IaRa. Ia is 72, Ra is 0.3. So this will be 0.3 into 72, so 21.6 plus 240, 218.4 volts. So EB is 18.218.4 volts. Now if like I have to limit the current, right? During plugging, what will be the armature current? Ia dash will be Vt plus EB divided by Ra plus R external, right? This current should be limited to 1.2 times the rated current. So 1.2 into the rated current, that is 72 amperes. So Vt is 240 plus EB is 218.4 divided by RA. RA is 0.3. R external is the one that I have to find out. This should be equals to 72 into 1.2. So 72 into 1.2 into 240 plus 218.2, okay, minus 0.3. So almost it will be 5 ohms. So your R external will be 5 ohms almost. This is the part A. What about the next part? In the next part, the braking torque produced. What will be the braking torque produced? Again, right? Braking torque will be combination of both the plugging torque and the load torque. So what is the load torque? Initially, the load torque was equals to the developed torque. So it was developing in rated condition. So I know the power rated, right? I know the speed. Okay, I know the EB. I know the IA rated. So from there, I can easily find out the load torque. It will be EB into IA divided by omega rated. So EB was 218.4 into IA. IA is the armature current. Armature current is 72 divided by omega R. Omega R is okay, like rated speed in revolution per second is 1500, right? 1500 rpm. So what will be the omega value? So omega rated will be 2 pi n by 60. So this will be 2 into pi into 1500 divided by 60. So this value is 218.4 into 72 into 60 divided by 2 into pi into 1500 almost equals to 100 Newton, 100.1 Newton meter. Okay, 100.1 Newton meter. Okay, so now what will be the plugging torque? So plugging torque will be basically, it will be EB into IA dash divided by, still it is rotating in the same speed only. Okay, so still this value will be there, 2 pi n by 60, right? So this I can write here, omega r, because during plugging at that particular instant the speed is not instantaneously changed, still it will rotate in the same speed. So this EB is same only, EB is 218.4, but IA dash is changed, it is basically 1.2 times 72. So 1.2 times 72. So basically, right, this torque will be, if I want to calculate, 218.4 into 1.2 into 72. Okay, that is also same, right? Basically it will be 1.2 times the previous one, right? It will be 1.2 times the previous torque, that is 100.1. So it will be 120.12. Okay, basically everything is same, just another factor of 1.2 has came. So this will be 120.12 Newton meter. So overall the torque, right, torque will be TP plus TL. So it is 120.12 plus 100.1. So this will be 220.22 Newton meter. Okay, this will be the answer for the part B. This will be the answer for the part B. Part C, the power drawn from the supply during plugging. So what will be the power drawn from the supply? Power drawn from the supply is, it's very simple, right? It's very simple. Power, what will be the power drawn from the supply? It will be simply VT into IA, because it is a DC circuit. IA dash actually, because the current has changed its value. So VT is 240, I guess 240, and IA dash is 1.2 times 72. So 240 into 1.2 times 72. So this will be 240 into 72 into 1.2, basically 20.736 kilowatts. So a bit higher than the rated power, okay, that the supply will provide. So that was it basically for this question. This is the answer, third answer. Let's now move on to the last one. Plugging is typically employed in what? Only small motors, small and medium sized motors, exclusively large, all types of motors. So generally plugging is used in smaller motors. Why? Because if I use it in larger motors, there will be huge power wastage, right? You just see the example in the previous case. The rated power was 20 kilowatt, and all of this power, right, was getting wasted. I was wasting 20 kilowatt of power, because it is not like the motor is supplying the terminal. The supply is providing this power, right, more than the rated power. So much power is getting lost. So if the rating is higher, then so much power will be lost, more than the rated power. I don't want that, right? So generally plugging is employed in small motors. In larger motors we can use rheostat braking, right, in conjunction with plugging. So it's kind of a mixture. Okay, so yeah, that was it basically for this lecture. I hope you have enjoyed this lecture, and in the next lecture we will be discussing about starting of DC machines and parallel operation of DC machines. So thank you for watching, and I will see you in the next lecture. Until then, happy learning.